Let's continue on with the second part of Chapter 2, which is on capacitance. We'll look at capacitors and how they're constructed and how we can determine the amount of charge that is held on a capacitor. And then we'll also look at capacitors and circuits and just how we deal with these capacitors and circuits mathematically. And then finally we'll look at some uses for capacitors when you pair them with resistors and how you can use them for time repeating circuits and also for storing energy. So first of all, the type of capacitor that we'll deal with is a parallel plate capacitor. It's the most common type of capacitor. It consists of two metal plates. Of an area A separated by a distance D. So two metal plates with an area A separated by a distance D. And when connected to a battery, the capacitor becomes charged, and it stores energy that can be used later. And that's primarily the purpose of a capacitor, is that it can store a large amount of energy that can be used later. I want you to watch a little video. This is just an interesting use of capacitors that you found on the internet. You can find almost anything on the internet. But this is a guy that replaced the battery, his lead-acid battery in the car, with a series of capacitors. Now, it operates in the way it functions is the same, but it operates in a much different way. So, whereas the lead-acid battery would take a chemical, what's the word? A chemical reaction, excuse me. Take a chemical reaction to convert this chemical energy into electrical energy. The capacitor works much differently. Instead, it stores electrical energy, and then it saves that electrical energy for later. So when you crank it up, your alternator runs, and it charges up these capacitors. And then your car uses that electricity while it's constantly charging. Then when you turn your car off, you have these capacitors that are charged. And then next time when you come to crank up your car, you can crank it up with that stored electricity. So there's no chemical process going on here. This is simply storing charges on two metal plates. So you can watch that little video here. The video is kind of long. It's about 10 minutes, but you can just watch the first few minutes just to get the gist of it. It's fairly interesting, I think. So you can watch that here. As I said, just watch the first few minutes. All right, now, so a capacitor is made up of two metal plates. They have an area A, and they're separated by a distance D. When you hook them up to a battery, they get a certain amount of charge, and so I'll get positive charges over here. These charges come off of the positive terminal of the battery. We'll talk about sort of how we think about electricity in circuits, but in general, when we talk about circuits, we're going to talk about the flow of protons instead of electrons. So you can imagine, and it's not really what happens, but you can imagine that protons actually flow up this wire and fill the plate so that the plate becomes positively charged. Now, the plate does become positively charged, but not for that reason, okay? And then we'll get an equal charge over here that is negative. So we get a positive charge here and then an equal but opposite charge over here of negative Q. Now, we can determine the capacitance of the capacitor is defined by the amount of charge it holds for a given potential difference between the plates. Potential difference, I'm going to write this in parentheses, potential difference between the plates. So just to remind you, let me go back to that previous page. When we talk about potential difference, it's the potential between 2 points. So for example, if this is VA and this is VB, my change in potential or my potential difference is going to be VB minus VA. And also remember, when we're talking about potential, that's a measure of energy per charge. So this is a difference in the amount of energy per charge for a given charge. All right, so we can express that. This definition is going to be Q divided by delta V. And this is our definition of capacitance. Now, we will take this expression and use it quite a bit, but we'll write it generally like this, which is just that expression reorganized. The units of the capacitor or capacitance are the farad. This is abbreviated with a capital F because it's named after Michael Faraday, which, if you remember from the video, that Einstein video, Michael Faraday was very important in the development of how we think about electricity today. So if you haven't watched that, it's not required for you to watch it, but I think you might find it fairly interesting. And 1 farad is equal to 1 coulomb per volt. And so, for the above figure, if the charge was 24 microcoulombs, and, for that figure, we had a potential difference across the battery of 12 volts. If the charge is 24 microcoulombs, then we can calculate the capacitance, Q over delta V, is going to be 24 microcoulombs divided by 12 volts. And that's going to be 2 microfarads. Notice what I did here with the units, by the way. I didn't convert this to times 10 to the minus 6 to coulombs. I just kept that micro, and then when I carried on into the answer, I remembered it, and I expressed my capacitance in microfarads. Micro will be a very common unit. Microfarads will be a very common unit for our capacitors. A 1 farad capacitor is a really big capacitor. Usually in circuits, we're talking about microfarads or even smaller capacitors. All right, here's a quick test question. Why don't you try that out? See how you do on it. You can go and record your answer here if you like. Now, for a parallel plate capacitor, the capacitance is dependent upon the geometric proportions of the 2 plates. So if I have these 2 plates, and they each have a plus Q and a minus Q, how can I increase the amount of charge that those plates will hold? First of all, how does the amount of charge affect it if the area is increased? If I make the plates bigger, how does that affect the amount of charge they can hold? Now, I think this actually is on your quiz, but I'm going to give you the answer because it builds up to something here. If I make them bigger, then as you can imagine, I can fit more charge. There's just more area for charges to be on. So if I make the area bigger, then the capacitor can store more charge. What if I increase the separation in the plates? So initially I have 2 plates that are separated by that distance, and then I take them and I separate them by that distance. How does that affect the charge? That might be less obvious to you, but as you separate them, it's going to decrease the amount of charge. The capacitor can store less charge. You have less of a potential difference there because you're separating them more and more, and so the capacitor can store less charge. Or excuse me, I'm sorry, you have more of a potential difference. Is that right? Yeah, you have more of a potential difference. No, never mind. You have less of a potential difference. No, never mind. That doesn't really make sense at all. So anyway, the capacitor can store less charge when you make them further apart. Okay, so we can develop an expression for C that is dependent upon both the area and the distance. So remember, we have this direct proportionality between capacitance and area. That is, as the area goes up, the capacitance goes up. And we have this inverse proportionality between the distance between the plates and the capacitance. That is, if D goes up, C goes down. And I can express this mathematically. It's just going to be C is equal to A over D. And we're going to have a proportionality constant, which is called the permittivity of free space, E0, epsilon naught. And this is the value for that. We're not going to get much into this. So if you recall, this is going to be based, or is going to be similar to our Coulomb's constant. You might see this somewhere else. That Coulomb's constant is equal to 1 over 4 pi epsilon naught. So those are related, the permittivity of space and the Coulomb's constant. So this is a separate expression. This is not the definition of capacitance, but given a capacitor with certain geometric dimensions, you can calculate what is the capacitance, what is the ability for that capacitor to store charge. Try this quick test question. You can pause and mark your answer here. All right. Now, let's look at one thing, dielectrics, and then we'll pause this screencast. The dielectric is an insulating material that inserted between the plates for a capacitor, and the dielectric serves two purposes. All right, the first purpose is it's to increase the capacitance of the capacitor. To increase C. So let's say I have a capacitor with no dielectric, and then I put something in between it that is a dielectric. This insulating material, it can be wood, rubber, paper is a very common material because it's a good insulator, it's cheap, and it's very flexible. And that increases the capacitance by an amount called the dielectric constant. So this kappa is the dielectric constant. The dielectric constant is always greater than 1. The dielectric always causes an increase in the capacitance of a capacitor. The second reason, which is more practical, is to keep the two plates of the capacitor separate. If you have a capacitor, like one of these electrolytic capacitors, you can cut it open and look on the inside of it, and you can see what they look like. I have a picture here, but generally you have these two plates. They're attached to some leads, and then you put this material in between them, right? And then you're going to take this and you're going to roll it up like a wrap from Roly Poly. Probably not many of you probably don't remember Roly Poly, but it was, I don't know, 5 or 6 years ago that we had it here. But you take it and it looks like a wrap. So my plates will look like this. Plates. And then my paper goes in between them to keep them from touching. Oh, this is like one of those wacky things. And then you can have an additional sheet of paper to keep those plates from touching. Ooh, you're getting very sleepy. Okay, so anyway, it looks like that. I have a little video and actually have a picture here. That's the inside of a capacitor. You have two thin metal foil plates separated by paper, and they roll them all up like that. Let's see, finally, I have a video. Here's a quick test question, which you can take a look at. But then I also have a video just about the insides of a capacitor. It's a fairly interesting video. I think it's 5 or 6 minutes long. And they actually blow up capacitors and look at capacitors and talk about what capacitors do. So you can watch that here. I think we'll pause there.